Hello and welcome to 29th lecture of the course on data-enabled tribological engineering from experiments to predictive models. Topic of this lecture is data-driven models for tribofilm formation. We have covered this tribofilm a number of times in various lectures. So let me first again provide overview of tribofilm formation. In lecture 1, we classify in thin lubrication and thick lubrication. And then we also define tribofilm formation is something like a generation of a film, it can be thick or thin, of materials. Now this material can be solid lubricant, can be liquid lubricant, can be gases also. This occurs generally at the interface between the two surfaces which are in a tribo context, or maybe say there is a load and as a relative speed also. What's the function of tribofilms? We say controlling friction. I can write also the reducing friction, but many times we give better word, we say controlling friction, preventing wear or maintaining minimum wear or eradicating the wear, and in addition providing the lubrication. So basic purpose is a lubrication, and through that we are trying to control the friction and wear. Why we are doing it? To improve the performance and durability of the tribo systems. What are those tribo system? It can be engines. There are so many parts in engine. It can be bearing. There are number of type of the bearings, number of type of the gears, cam follower mechanism, and so on. How do we know the effectiveness of the tribofilm? We say effectiveness of the tribofilms depends on its composition, and whatever the film which is getting formed, composition of that. It depends on the thickness. Earlier we were talking about thick lubricant layer or tribofilm, but now we are talking more or less thin lubricant layer. What will be the adherence of this tribofilm to the surfaces, and what will be the compatibility with the operating condition? One is that if it doesn't remain on the surface, it gets removed during shearing action or sliding action, then it is not effective. Tribofilm is not effective. Second, if we are applying some sort of a lubricant layer or tribofilm, and then because of the high temperature, because of the high humidity, or because of the some sort of erosive particles, if the tribofilm doesn't remain, again the effectiveness will come down. Now coming to the composition, mostly we talk about structure. See, now it can be oxide, it can be sulfide, it can be phosphate, polymer, nanoparticle, apart from liquid lubricant or air lubricant. Now we know very well in environment oxide formation may occur, but sulfide and phosphate we generally add the additives in a lubricant to form those kind of tribofilm. Polymers also we can use as a solid lubricant, and many times we use nanoparticle, we add nanoparticle, so the nanoparticle are able to form the tribofilms. Now what are the factors which are affecting the tribofilm or formation of tribofilm? We say it depends on the contact surfaces. Is it a convex and concave surface? Is it the convex surface? Is it a flat surface? Is a flat versus convex surface? It depends. Then comes a lubricant chemistry, whether the lubricant layer is a very long carbon chain, it has some sort of agents or not. Operating condition, as I mentioned, the low temperature, high temperature. Many times at the extremely low temperature, lubricant doesn't work properly, or the high temperature again doesn't work properly. And other environmental condition also will affect it. So what we do generally, we say tribofilm can be classified in various categories based on a specific film thickness. And then if this film thickness is not sufficient, during sliding the film thickness wears out. Then what will happen? There is a chances of adhesive wear, and that was covered in the lecture 4. In lecture 6 we say we can dry chemically bonded layer or physically bonded layer or attached to the layers. In the interface we can use a lamellar solid, we can use a pressurized fluid. Fluid can be hydraulic fluid or maybe say lubricant, base oils, or can be the air also. Now it can be self-acting or it can be pressurized. Both the things are possible. So we have various mechanisms to form the tribofilm. It can be thin, it can be extra thin also. It can be solid lubricant related, it can be air lubricant related also. It can be chemically agent which are interplaying in between the surfaces or interface. So we have variety of tribofilm which can be formed at the interface. Three typical thing which we have shown in lecture 8 when we were discussing about the mixed lubrication. What's a mixed lubrication? We say mixed lubrication, the solid metal to metal contact also will occur, and as well as we have agents which are separating the surfaces. So it's not completely separated, fully separated. Few places the lubricant layers are active and few places lubricant layer are not very active. We discuss about the physical adsorption. This is a what addition, and we say there is no problem as such. But then chemical absorption and then chemical reaction also. We consider the three different aspects of the thin layer. One is the physical absorption, works at the lower temperature. At the high temperature, this physical absorption becomes a weak, and then it has to move towards the chemical action and then chemical reactions. So what we say, when a thin lubricant film is present at the interface, friction decreases, or we can control also. Lubricant forms a protective boundary layer between the moving surfaces by physical mean, that's a physical adsorption, or chemical mean, that means chemical action or chemical reaction, to reduce a metal to metal contact and prevent excessive wear. If it is possible that most of the time it is covered by the lubricant layer in form of physical adsorption or chemical adsorption, then the friction will be lesser, wear will be lesser, and our ultimate aim is to save energy and reduce the material loss. So both the things will be possible when we are thinking carefully about the tribofilm formation. So what we say, lubricant chemistry plays important role. Adherence to the surfaces, when we give a lot of emphasis on that, that also plays important role. What is lubricant chemistry? We say reaction at the interaction between the surface molecules, lubricants, contaminants also, and other species which are present in environment. There are a number of actions which we have also covered in previous slide. We say polymerization may happen, oxidation may happen, or other kind of the chemical reaction may happen. Coming to the adherence, we say attachment to the surfaces. It can attach to the surface. However, there is a difficult problem comes. What will be the growth? If there is a thicker layer, thinner layer, that matters more. Reason being, we know that every surface is a rough surface. Its asperities are higher of a magnitude compared to the tribofilm. Naturally, the film will get ruptured and friction will increase. So that's an important aspect. Another thing comes when there are wear particles, and the wear particle or the soft particle under compression, they may form the lubricant layer also, and they get attached to the surface. So if that is happening, that we will be requiring it, and many times it is a transfer layer. That means a metal surface is there, and then if we are using the polymer against that, polymer gets transferred to the metal surface, it get adhered to the surface, and it can form a tribo layer or tribofilm formation occurs there. So that's always important. What are the properties which we really want to see? We say that this tribofilm should be hard enough so that it can bear the load. It should be elastic enough so that it doesn't really get tear away from a surface. It should have a sufficient adhesion strength to get attached to the surface. However, it should have a minimum interface shear strength to minimize the friction. So we have some desirable properties requirement from a tribofilm formation, which is really required to understand, which we have already covered in number of lectures, so that we are overall able to make a good surface, good lubrication, good tribofilm formation at the surface. Now this also was covered in earlier. We say, and when the load is smaller and temperature is lesser, Even the dry lubrication, natural oxidation of the surface will be sufficient to provide a tribofilm. However, if the load increases or temperature increases, we can go ahead with the liquid. It can be water also, it can be any liquid. However, if further load increases or temperature increases, we should add the friction modifiers. Then liquid will not be sufficient. We need to use a friction modifier like ammonia to graphene into the liquid, so that liquid carries those friction modifier to the desirable surfaces where the tribofilm formation is required, and then this FM will reach to their form of tribofilm and prevent the metal to metal contact, will reduce the friction, it will reduce the wear also. Further, if the load increases and the temperature increases, we really require anti-wear additives. Similar manner, if further load increases or temperature increases, we really require extreme pressure additives. So this all have been already covered in our earlier lectures. This was also covered in a lecture 9, particularly when we are thinking about tribofilm and the film thickness is being given, like in this case H1 and H2, and then we say there is some sort of convergence, then only the pressure generation will occur. And we discuss a pressure generation mechanism. We say converging, diverging mechanism is one, squeeze film formation is another one, hydrostatic or aerostatic is third one, and everything can be governed by the Reynolds equation, which we have covered in this lecture. We also covered two different geometries. We say that convex and concave. This is a convex and this is a concave surface, and they come into contact, and we this kind of bearing was named as a journal bearing, and we know that initially it will move in opposite direction, resist a force, and after that it will get stabilized. That means after few rotation, this geometry will get stabilized, will be able to self generate the pressure, and that can be explained easily. Another one, we use a word convex or convex. In convex or convex, we say there is a possibility of elastic deformation. So here it is only the fluid film lubrication happens. In this situation, fluid film lubrication plus elastic deformation will form a film thickness, or we say tribofilm formation, and that was shown using this kind of diagram. This was covered in a lecture 9. We say when we have a cylindrical contact, two surfaces are in a cylindrical contact, this kind of a formulas can be used. Is a heuristic formula or empirical formula which can be derived with this relation also after taking a lot of assumption. We also discuss something about sensitivity. We say that W or applied load has a lesser sensitivity compared to the relative speed. Speed has a higher sensitivity, it will affect more. If I'm increasing speed, it will have much more effect to increase the film thickness. If I'm increasing the load, it may also reduce the film thickness, but not to that extent. So this was a for cylindrical contact. Further coming to the ball on ball surfaces, where we know that the K factor also comes because of the elliptical contact, and that can be utilized this manner. And I also say that the complete expression or complete chapter has been given in this my book, which was published in 2016. So tribofilm formation has been dealt in our course in detail, and now trying to summarize and trying to show the couple of more informations or techniques which can be utilized. We also covered stripe a curve. We say the thin to thick lubrication. This was also covered in lecture 6. We say initially when it is a boundary lubrication, we talk about lubricant chemistry. When it comes to the hydrodynamic, we talk about the lubricant viscosity. However, there is a trend thick to thin. That means we are moving towards this side as we are going with a better and better science. So this is very important, and this is why it is required, because we want to improve the machine efficiency, which is clearly seen from here. We have seen shown that coefficient of friction in hydrodynamic lubrication, as the speed increases, coefficient of friction will increase, which is not desirable. So we wanted to maintain the coefficient of friction somewhere in this region. Naturally, we need to reduce viscosity. Whenever you are using a lesser viscosity, there is a chance that this may go to this side in transient condition and may damage the surface. So that's why the tribofilm formation is very important, particularly when we are moving from thick lubrication to thin lubrication. We are not happy with hydrodynamic lubrication, even though it is causing a minimizer wear as almost zero wear, except the start and stop. But still, we want to save the energy, and that's why we are trying to reduce the viscosity. And almost all engines now they are trying to reduce the oil viscosity to lesser extent, and that is causing chances of mixed lubrication, boundary lubrication, particularly when the load is high and speed is low in the situation. We covered this diagram in lecture 8, particularly for the mixed lubrication. We say very well now it is very difficult to keep whether it will be hydrodynamic and whether there will be a mixed lubrication or boundary lubrication. So complete oil should have everything, or it kind of self-adaptive. Now if we should have a low viscosity oil, and then we add FM, we add anti-wear additives, we add EP additives. So whenever there is a situation, below viscosity oil will be able to do justice to the hydrodynamic lubrication. FM additives will be able to do a justice when there is a somewhat mixed lubrication. And then when coming to the slightly higher side, load is on higher side or speed is on lower side, anti-wear additives will be playing an important role. When that is almost specific film thickness is lesser than 0.1, then EP additives will work in a bigger way. So this was a covered, and then that's why the most of the now oils they contain additives. I have heard that many times additives are even up to 10% base oil and 10% additives. Of course, with the every additive whenever we mix, lubricant cost will increase. So again, if we have better science, better knowledge, the cost can be controlled based on that. That's why we see no traditional models of tribofilm formation like boundary lubrication, in which particularly the thickness is significantly smaller than the composite surface roughness. We also covered the surface roughness aspects. We say if the surface roughness is lesser, there are more chances to improve the lubrication. That's why the specific film thickness plays important role. Now, if it happens to the mixed lubrication, again the surface roughness will play important role. However, if it comes to the hydrodynamic, hydrostatic, aerostatic squeeze and elasto-hydrodynamic lubrication, surface roughness may not play very important role. So in other words, we say particularly in this zone, surface roughness doesn't play important role. While in this case, the surface roughness of the both the surfaces will play important role, and we need to keep in a check. And trend is going from thick lubrication to thin lubrication. That means we need to really think about more and more additives and better surface softness. Both the things are very important. Now in our models, those should be also accounted. Question comes, how do we account so many factors? And when we are considering about tribology, or when we are considering the tribofilm formation. Now, question another one comes that how do I analyze? One is a striped cow. We also covered this wear debris collection and wear debris analysis to figure out what is really happening. We said that if the wear debris are lesser than 40 micron, we may not worry. However, this again is subjective, depends on the size of the component. Many times, if the wear debris is lesser than 10 micron, satisfy reason being it is a only the initial wear is happening, or there's only surface roughness which is there, it is getting polished. If wear debris are increasing in size and then further increase in size, so when it comes to the medium range, we can say it is a mixed lubrication. If it is going on much higher size, then we can say it is a boundary lubrication. So this is a way we try to quantify what is really happening. If there is no wear particle, or once in a while it is happening because of the start and stop, we can say that the lubrication mechanism is in hydrodynamic or aerodynamic or aerostatic, hydrostatic or elasto-hydrodynamic lubrication mechanism. But if there are number of particles and the size is reasonably on a higher side compared to the minimum size which we quantify, then we can say there is some sort of mixed lubrication. If number of particles are increasing significantly, then we can say it's moving towards a boundary lubrication, where the specific film thickness is much smaller. It is like a point lesser than zero point 0.1. So this is a way we can really classify based on the data which can be captured in situ for the monitoring. So that's why we say we discuss inline monitoring, online monitoring. This was already discussed in lecture 18, and this was shown in lecture 22. So that's why we say lubricated contact undergoes a running in, and when it is undergoing the running in, the number of particles will be lesser or more, but size will be much lesser during the sliding. However, one important point comes, whatever theoretical modeling like I do initially, I'll count some surface softness which is measured from in a lab. But when we are making a contact, or when we are really developing a tribo contact and real situation, surface softness will change. Either we should model it, or we should capture the images and do analysis of images, and then we get a solution. So there are a number of ways we can directly capture image, or we can go ahead with the thermal imaging and then capture, and then we take indirect measurement, whether the heat is increasing or temperature is increasing, indirectly friction is increasing. So I can measure the friction, or I can measure the temperature, and indirectly can figure out what will be the tribofilm formation. How is it really beneficial? It is really going in the wrong side. It is causing the wear out of material, and then it will lead to the failure. So we have both the options so open, and uh, when we initially do all this modeling, it is good for the designing purpose. After that, we need to go for in situ measurement, and in situ measurement we really require a tacit knowledge which already we have, or knowledge which we can extract from a literature, and we make that knowledge in kind of some sort of predictive models, then use a predictive model with in situ measurement using the sensors to get overall good results. So that's why we say machine learning can be used to predict and optimize tribofilm formation processes. In tribofilm formation, ML techniques can identify correlation between inputs. Now we need to choose what are the input parameter. For that, we need to do sometimes sensitivity analysis, which will be dealt in the lecture 33. Now what are the input parameters? We know the load, we know the speed, we know the temperature, we know the lubricant composition. Another other possibilities is a misalignment, which we'll be also discussing in the present lecture. And another one is a tribofilm properties, with what will be the thickness, what will be the composition, what will be the addition. So initial some models are fairly required, which can be updated or changed as per the situation. So those things can be rectified and improved based on the data which we collect in situ measurement. Now, I'm just trying to cover one research publication which was published in 2022 in Tribology International, where they indicated transition from boundary lubrication to hydrodynamic lubrication, and the paper title was a simplified approach to prediction of mix and boundary lubrication. Ideally, we don't want mixed lubrication, or I don't want boundary lubrication, but when we do a friction measurement, and then we know that to overcome this friction we really require more lubricant power, and overall energy losses will be on higher side. So we need to take a decision. So this factor X factor has been given as a friction coefficient of friction measured in EH condition, and this is a maximum friction, and then plot it as a function of a specific film thickness. So this is what has been done in this case. You can see here, when a specific film thickness is lesser than zero point 0.1, more or less it is a boundary lubrication is dominating, almost this equal to the 1, that means F is almost F0, equal to F0 maximum friction. Now as specific film thickness is reaching to the 1, we are able to see the reduction. This fraction is almost 30 to 40%, and then at the 10 it is almost 0. That means we do not have any mixed lubrication. However, this will vary from one setup to other setup. However, in this Taylor has a given that we can go ahead with standardized friction curve to differentiate lubrication regimes. If we want to know classical lubrication, when shall I use hydrodynamic, when shall I use elastrohydrodynamic, when shall I use a mixed lubrication, we can plot this kind of curve, figure out what is the operating range, where that is really happening, and we can calculate based on that. However, they also found there are some errors whenever we start measuring something. There will be some inaccuracy that will bring some sort of uncertainty. That will also be discussed in the lecture 33. We will be discussing uncertainty analysis. However, in this situation, it's very clear that they want to take input from a load, speed, and temperature measurement. They also mentioned that when the specific film thickness here, the lambda is a specific film thickness, is a range of 0.01 to zero point 0.1. That's what we have discussed over here. This sometimes is known as a reverse S curve. So if you want to go through literature, you can figure out how do I differentiate between hydrodynamic, last rod hydrodynamic, mixed lubrication, boundary lubrication. You can refer to the reverse S curve, which is shown in this manner. In this case, you can see here, this is the reverse S curve, and then we can plot it and we can get a good results from this. So this is the one method that when we are very knowledge of the classical or old technologies of tribology, we know what is a hydrodynamic lubrication, we know what is a elastrohydrodynamic lubrication, we know what is a mixed lubrication conditions, and then if you want to just know how to apply and where to apply our algorithm so that overall we can estimate the tribofilm formation, we can utilize this kind of technique. However, to include a mixed lubrication as a formation, because we know the hydrodynamic, elastrohydrodynamic, and boundary lubrication. The tribological study of elastomeric bearing of marine propeller shaft. I'm using the word elastomeric, reason being elastomeric are to some extent subjected to elastic deformation, and I'm using word, this is a case study, and then we did some sort of analysis, and then we got the data from a logbook and the worn out surfaces, and based on that we try to give some sort of recommendation so the future failure of those bearings should not happen. So I'm again going to discuss this one. However, now in because we have a improved image analysis, understanding of images, this can be further improved using ANN or image analysis. So to some extent I'm highlighting those aspects. So what was this case? Elastomeric material was used for the bearing, and we did a case study for Indian Coast Guard ships. We understood that the mixed lubrication analysis is dominating here. Reason being, the lubricant was used as a sea water lubricant, which also contains some sort of particles. We realized that those bearings are subjected to unequal and non-uniform wear of the bearings, and because of that, often after two cycles they need to change the bearing, and each bearing is costly. It takes time also, the layoff happens, they need to stop the ship for the few days to change it. To predict that well in advance, we made a computer program which has been completely given in this publication. So we developed computer program to estimate ribofilm thickness and anticipate the what is the lubricant regime. We got the data, we got the data related to the dimension, and we could calculate a geometrical clearance, not only fresh, even the old bearings which they have replaced. Also we found the data for the operational conditions, what will be the load, speed, running hours, because we got their hold of their log books, and which was also shown, and one of the slide I'll show those kind of data also. And we also did some measurement in a lab, particularly dynamic viscosity of the salt water. We know that many times we take a assumption of the Newtonian fluid, but it doesn't happen in reality. And here the even water is subjected to the non-Newtonian behavior. Its viscosity increases with the velocity. We also observed that they have a surface softness of the bearings and shaft, which can be accounted for our analysis. Even the particulated contamination that also should be accounted in this case, so that we are able to predict the accurate results. And finally, recommendation to ensure the appropriate functioning of the bearing system to minimize the wear. Again, we are saying that to keep a wear below certain limit, because these bearings are designed for the 20 years, it is not for the infinity years. So there will be some wear, and we can estimate and we can try to figure out what will be the residual life of the bearings. So this is again this figure and the complete thing has been picked up from this literature 2009, which is my own publication. We used and as I say that we selected this ships, and which has a two propeller shafts and driven by the 6400 HP engine. Each propeller shaft length was around 24 meters, weight around 10 tons. The propeller shafts were supported on a four bearings total, and thing is that the bearings are plain. You can see here these bearings are plain here, but on the top they have a grooves. So that has been shown here. Upper half has a groove, and the lower half doesn't have a groove. It is a completely plain, while here top one is the having a grooves to circulate onto to the move the water easily in this situation. And this is a arrangement has been shown, a bearing arrangement. This is a propeller has been shown in this manner, which is really required. Now we analyze the three ships. We say first ship, that's a summer ship, second Sangram ship, third one is a Sarang ship. First ship was commissioned in 1995, second ship in 1997, third ship in 1999. But failures are more or less same. They experienced consecutive bearing failures on both the shafts over two operational cycles. So you may using the word two operational cycles. That means time which is between the two successive docking. So it has gone and come back, and next gone and come back, and then after that the bearings were supposed to change. Same thing happened in a Sangram also. They found comparable failures in both the shafts, and by two operating cycle, and only in one case they also changed in one cycle also. So it is more severe in this situation. And same thing again in 1999. Now what we can say, elastomeric bearing used in all three ships, Samar, Sangram and Sarang, were specifically designed by the company Thornton Bearing Company, which is a well-known company. They make this kind of bearings, and then they can also refurbish these bearings if the bearing is worn out. To avoid the bearing wear, we know that bearing should operate in a hydrodynamic or elastohydrodynamic lubrication mechanism, but because their bearings are very wearing out well before the time, that means hydrodynamic or elastohydrodynamic lubrication is not happening completely, it is happening partially. And this is what we have been seeing, the bearing wear. Bearing operates under mixed lubrication. Of course, it is not in a boundary lubrication. We analyze it as a mixed lubrication. We also we say that some load is being taken by asperities and some load has been taken by hydrodynamic or elastomeric lubrication. Now question comes, so why the bearing failure happens? So we estimated initially bearing failure. We say operating shaft speed sometimes there is a lesser than 100 rpm, and 100 lesser than 100 rpm is inadequate to create an adequate triboform. That means speed is lesser. Even as I said, EHL is a little more sensitive towards the speed. If you reduce the speed, naturally EHL formation will not occur. Even hydrodynamic lubrication doesn't occur. And second thing is that after initial wear, what will happen? The radial clearance of the bearing increases. And earlier one of the lecture I mentioned very clearly, if the radial clearance increases, load carrying capacity will reduce significantly. So this is also a very sensitive parameter which we have discussed in earlier lecture. Last one is the impact of the particle contamination in a seawater. We know very well seawater will have some particles. It cannot be free, and then there will be some sort of roughness which is causing us some failure. So we need to really see the impact of this lesser speed higher clearance and some sort of particle contamination or roughness, because particle contamination will create a three body abrasion, while roughness can create a two body abrasion. So those things are important. That means we need to simultaneously use a pressure equation as well as a wear equation, and we need to do iterative procedure to come up with the right results. However, as I said, in the future we can really take an image and then we can analyze the surface roughness, a change in the profile of the bearing, and then we can do a better analysis. Now, one of the major thing which we realize is the shaft is always some sort of misaligned. It is not getting perfectly aligned. So first assumption, when we use a hydrodynamic lubrication or elastohydron lubrication, we assume the shaft will remain aligned, which doesn't happen in most of the cases. To model the misalignment, we took this factor, that's what we call a T as a ratio, by is equal to m by c. This is a c is a radial clearance, and we found how much is the displacement from the h, and because we are assuming it is a centrally, or whatever m this side, m will be also on this side, so it is equally divided. So this m was measured, and then we say that in the situation, film thickness which we have been utilizing in the hydrodynamic lubrication mechanism need to be changed. What happens in a hydrodynamic lubrication? We take H is equal to 1 plus epsilon cos theta. This is a non-dimensional film thickness. While in this case we are adding one, that says Z is the axial coordinate. We are bringing axial coordinate, not only the radial coordinate, and this T is a factor and length is a bearing length. So that was incorporated into this. Another thing comes when there is elastic deformation, there will be increase in the overall film thickness. So again, there is a heuristic model. The film thickness can be improved in this form. This is because of the H bar is because of the EHL case, and this is because of the hydrodynamic case. Overall, you can see here this is a sigma, which is a composite surface roughness, and this is a film thickness because of hydrodynamic. It improves to some extent. Again, this is a heuristic model. Actually, when we take a more and more data using the machine learning, this kind of relation can be improved significantly. Now, four bearings overall, as I mentioned, 1, 2, 3, 4 bearings in this case. All cases are the photo lubricated bearing. Of course, they had a 5 and 6 bearing also, but those bearings are mostly oil lubricated. In the case, you can see first all the four bearings are of the same length, 735 mm, while oil lubricated bearings have a length 190 mm. However, we are not going to use this bearing, we are going to consider only this bearing. There is a change in the shaft diameter. In a bearing 1, shaft diameter is 365 mm, shaft diameter in the second case is 355 mm, third is a 350 mm, and fourth is a 345 mm. As it moves away from the one end, that shaft diameter is reducing. But major problem becomes the load. The first bearing load is almost a 60 kilonewton, while coming to the second, it is a somewhat lesser, or maybe lesser than 50%. But second, third, and fourth, they are load is applied, load is more or less same. So only first case is a severe case where the more and more bearing damage may occur. Reason being the load is very high, and we are keeping same shaft length. Of course, to some extent we have improved the bearing diameter, but that increase in bearing diameter, now, which is not hardly any 5%, cannot really sustain a load which is more than 2 times. So this is what the first observation from our side. We develop a complete algorithm. You can see we started assigning this completely MATLAB code, acquire the parameter which is really we need to assign. We initially gave some sort of eccentricity ratio, which was earlier mentioned. In this case, we gave some eccentricity ratio initially, and we do iterative procedure. Based on that, we calculate the pressure, integrate pressure to the find out the load. We compare the load, and then if there is a load is lesser, we increase the eccentricity ratio. If load is on higher side, we decrease the eccentricity ratio. And then if they are really converging to the same level, we try to figure out what will be the film thickness. Now here we assume something what we call as a specific film thickness. We say specific film thickness is a greater than 3 or specific film thickness is a lesser than 3. Now this is an assumption. It can be 4, it can be 5, depends on the surface roughness. However, literature mostly says that 3 is a sufficient or it will give a reasonably good results. Again, as I say, there may be surface roughness on the higher side, then we need to do think slightly different manner. While in this paper we assume specific film thickness greater than 3, it can go to the HL or elastohydromet lubrication. We try to get the results and converge it. However, if specific film thickness is lesser than 3, which is happening particularly for in this case, particularly the bearing failure happened within a 2 year time or within 2 cycles of that. So what we see, what is really the film, what is the wear out which we measured directly from a bearing, and then we try to improve cycle by cycle wear rate, so that finally it comes to the right solution. And here we could figure out what will be the time, and based on time we can find out what is the bearing life. Now we can estimate further that overall what is a permissible limit. Now, what's the meaning of that? Initially I suppose the bearing wear is only 0.3 mm, and then a permissible wear is a 1 mm. So I know that 0.3 mm how much time it took, and now using this kind of relation, when it will be equal to 1, using a theoretical calculation or simulation, I can find out what will be the bearing life. Now when we are introducing the misalignment, the major issue comes. You can see here when we are going ahead with the perfect alignment, you can see the pressure, maximum pressure is only 34 megapascal or 35 megapascal when we are going to slightly on a misalignment. But when we reach to the 0.01 degree, you can see it goes to the gigapascal maximum pressure, which is very high. And we also compared with the finite difference study, and we found a similar kind of results are there. That means bearing need to be aligned, otherwise whatever we do it will not give a solution to us, or bearing failure will occur. So first thing is the alignment of the bearing. Whatever we develop bearings, if the bearings are not perfectly aligned, failure will happen because of the misalignment. Now, whatever the good oil you use, what is the good material you use, best thing which you do, but misalignment creates a lot of problem. And then this is what we have shown the first results. Now when we are coming to the, when we assume this specific film thickness is lesser than 3, and then we need to use a wear volume calculation. You can see here this is a relative velocity, that's a sliding speed, then comes a time where we, because we need to estimate the bearing life, that's the time is really required for this purpose. K is a wear constant. Now this is a dimensional wear constant. In earlier lecture I mentioned these two things very clearly. When we use a dimensional wear constant, that means it is a K divided by H, where we are not accounting hardness, and this is a dimensional wear constant, and that's what has been given the unit meter square per Newton. So this is what we are doing. Now one more variable comes here is a asperity load. Even though we are saying specific film thickness is lesser than 3, whole load we are not transferring to the asperities. We are saying what is the load on asperities and how much load is being taken care by the hydrodynamic or EHL. So this divide was necessary to calculate or to estimate everything appropriately. Now based on this we use a curve fit equation, or equation we say localized film thickness is can be given as a 0.6 r2, that's a radius power 1 minus 1 by 3, length power minus 2 by 3, and this is a wear volume, in this case 2 by 3. So this has been clearly mentioned, but assumption is that wear of the journal surface is negligible. In actual case, there is a possibility of journal wear also. If it is, then we need to account two volumes, not a one volume. However, most of the time the bearing is a sacrificial material. The bearing wear will be dominating and general wear will be almost negligible. Now, this is what we have done by measurement of the wear. Again, assumption, what we are talking of the film thickness, if you look at this film thickness assumption, we are assuming everything uniform, and this was already discussed in the lecture 22 when we were doing the discussion of the 4-ball testing. And we say if you look at the 4-ball and the bearing failure, or maybe say ball failure, we are not able to see a simple chord. We are able to see the galling effect along with a wear. That means there are raised surfaces, and because of the raised surface there will be problem. That means surface roughness has to be estimated properly. And one more thing, as I mentioned, now when we were doing in 2009, that time this kind of techniques were not very popular. Now those techniques can be brought up. Take an image of the again those failed bearing and do analysis. Take a original image, go to the grayscale image, convert to the surface roughness parameters, and account those parameters into the film thickness calculation. That will give you the better results compared to what we got around 15 years back. And this was already covered in lecture 22, so you can implement this kind of suggestions. Now, returning back to the same publication, when we say we are using the wear equation, particularly for asperity calculation, our load is asperity, how do we find this? So that's why we say contact happens between the asperities, and we also need to believe it's not that only the asperities are going to bear the load. There's a possibility of EHL film formation, and that's why we use this ratio. That's what the pressure Pf divided by the total pressure, and total pressure can be P is equal to Pf plus Pa. Total pressure can be that way. So we have a separate calculation of Pf, separate calculation of Pa, and we know that this Pf calculation can be done, which we already covered in lecture 9 and 10. This is what the same film thickness has been accounted over here, and we know very well this pressure, whatever the EHL case we are checking, this will be significantly affecting the results. And here we are just simply saying 1 minus Pf divided by P. So asperity can be derived because we are already learned about how to find out the Pf calculation or pressure calculation. This was it covered, as I mentioned, in lecture 9 and 10. We say we need to go ahead with Reynolds equation, solve the Reynolds equation, and of course along with that we need to talk about the elastic equation, which can be used EHL case. Elastic equation to be solved with elastic deformation of the surfaces can be accounted. With this we can give some sort of completeness. Now when we counted all this, we try to figure out what are the which speed then the wear will turn out to be lesser, and that's why we plotted RPM versus the parameters. You can see here that as clearance changes, clearance 0.01, clearance 50% of that, clearance 50% of this one, and clearance 50% of that. So you can see here as a clearance is decreasing, as a clearance is decreasing in a bearing, that RPM is also reduced. We don't really require high RPM, but as the clearance increases, you can see that a high RPM is required. That means even in the beginning bearing is working well, quite possible after the some wear out, this clearance will increase. As the clearance increases, you can see here now initially the green color line, then yellow color line, then violet color line, then blue color line. That means operating speed need to be changed. If it is not changed, naturally there will be more wear, or it will again go to the boundary lubrication, or mix from mixed lubrication to the boundary lubrication. This is the same thing which was done also in surface softness. So here the major issue comes with the wear, clearance is increasing. Second problem, with the wear, sigma is also changing, the surface roughness is also changing. This also shows here the sigma yellow color line, that operating speed need to be on a higher side, and blue color line which shows a minimum sigma. That means it is a definite always that when this kind of bearing, initially when the bearings are new, it will have a better function, and as it progresses the wear out will be there, and that will impair the bearing surface, increase the clearance, and will cause a bearing damage. So after that we need to change. That means bearing wear is happening, only what we can control, make effective tribofilm to reduce the wear rate. That means instead of going for the 2 complete operating cycles, we should go to 3 or 4. That is a possible by reducing the wear rate. We also did a calculation for coefficient of friction, which we initially mentioned, shown kind of a reverse S cycle. We can figure out as the clearance is increasing, coefficient of friction is on a higher side. You can see here in this case, coefficient of friction, particularly this RPM. Here there is a low RPM itself, it is happening, and we find clearance is on higher, coefficient of friction also will be higher. Otherwise, even look at this one, then particularly the 1000 RPM, only the coefficient of friction is reduced. When clearance is reduced, here even 100 RPM, coefficient of friction is a lesser. So this the clearance plays a very important role. Same thing happens to the sigma also. In this case, we found sigma has a slightly lesser sensitivity compared to clearance. Clearance is very sensitive. You can see here the blue color line, then violet, then yellow, then green color. So clearance is a very sensitive towards coefficient of friction, and we need to control more on clearance. That can only happen when there is an effective tribofilm, and wear rate is almost negligible or ultra mild wear. This is what we got results from a logbook. You can see whenever the bearing was installed, initial clearance is a 0.75, zero point 0.6, while after 3 years the clearance has increased significantly. Similarly for bearing 2, but bearing number 1 clearance increase is significantly high. Bearing 2 is a relatively lesser. Third case, it's also increased 0.6 to this one. So third number bearing also even as a lesser load, but the bearing clearance has increased significantly. Coming to the second installation, first installation, second installation, third installation, every time we find that bearing is happening, and the bearing clearance is increasing, many times 30%, 40%, 50%, the load carrying capacity will be high. The ideal situation in this situation is to change the bearing, we bring a new bearing, otherwise the losses will be more significant compared to this. Another, as I mentioned, the viscosity measurement. When we say that the viscosity at the 150 rpm, you can see it is a 0.97, while in 250 we are able to see the viscosity thickening effect. So this is very important. Here the viscosity thinning, what we are understood in the oil cases, instead of that there is a viscosity thickening effect is coming. So these aspects need to be accounted, need to be incorporated in analysis, so that this data driven approaches really help. When we have a data, we are able to improve the solution, we are able to incorporate learning from a data, and what is the really behavior, instead of just assuming that there will be shear thinning effect on Newtonian fluid. So this is a non-Newtonian fluid, and every cases we are able to see the shear thickening effect is happening in this situation. In this case, almost all the cases shear thickening effect is coming. So this is important, particularly not only the increasing speed is going to help to reduce the friction, but shear thickening is also happening, which is increasing viscosity, which is also going to be helpful in this case. Data log also gives us some sort of cycles for because we analyze the total 3 ships. You can see here total number of engine operation, total number of clutch condition, number of start and stop. So we can also think about how the wear happens in the start and stop, that also can be utilized. And then even it shows on how many cycle it operated at 130 rpm, how many cycle it operated 143, how many cycles operated 156, 170. So these are the data which are really helping to improve the bearing solution. Now when I solve the complete algorithm, I had to write this as a case statements. The first this much rpm after this many cycle this rpm, after this many cycles. However, only thing is that we should know the history, how the sequence happens. That was a missing in the situation, because these are the data log book they are maintaining, but sequence has not been done sequential manner, so we can estimate, but it is not in a sequential manner, so there will be some error. And that's why we say that in situ measurement will be always a better results. Here we are able to diagnose failure and how the failure is progressing, but not in a complete sequential manner. Here we are able to see a overall wear rate, but it doesn't have a sufficient data, and that's why the in situ measurement will give a better results compared to this. And this is what we have done analysis, and we found that bearing 1 has an increased clearance, and it really requires a more operating speed compared to other bearings. However, that doesn't happen, and that's why that we need to either increase the overall idling speed of the shaft, because they have to have idling speed, and then idling speed, instead of going for the 100, if it is a speed is has moves to the 200, that bearing will failure will stop. Bearing failure will be almost negligible. But because idling speed on the higher side, it may causes some sort of more losses of the engine, or maybe say friction on the operating cycles. So overall, there should be a trade-off. What should be done, and this is very important to keep in mind: friction, wear, and energy loss. Friction and energy losses are directly related, but to many times to reduce the friction, we are pumping lubricant, we are pumping water from a sump pump, we are forcing it. That pump also will consume some power. We need to convert that power into the equivalent friction loss, and then when we sum up, whichever results is give the better results, we need to go ahead. The only the bearing, and the bearing replacement is very difficult, cost consideration comes, downtime comes, then we need to take an appropriate decision. That's why we say the bearing 1 is a more critical, and that need to be given more emphasis to analyze and come up with the right results. Now, as I mentioned, now we need to move to the on advanced techniques, because now we have machine learning. It is really helping a lot in a big way. We can, as I say, the pressure generation, hydrodynamic pressure generation, we can use a Reynolds equation. We can take some assumption, small bearing assumption, and then try to analyze it. Now we can use a machine learning, deep learning, or artificial neural network in this case to simplify the problem. Now, supervised learning, as I say, we have some knowledge, we have a tested knowledge that can be utilized, and we can think about experiential learning. Reason being, when we are operating with industries or companies, we require academic knowledge, but we also require experiential knowledge to be incorporated. And there, the machine learning helps in a big way to incorporate that experiential learning. That's what we call a supervised learning, and we have a model that can be done. And this is complete thing was already elaborated in lecture 24th. So what we see, the machine learning is a modeling methodology that encompasses the use of data. As I will say that when we are getting better and better data, we are getting better and better results. And then this data can come in any form. It can be coming in document. As we have learned from a logbook, we analyze a logbook and we got the data from that. So this is very important to incorporate a machine learning. And when we are talking about the predictive model using ANN, we have already covered a couple of case studies using ANN. I'm trying to repeat again. We say predictive modeling of tribofilm thickness involves generating mathematical models, because we can export that model for our purpose. And in one of the lecture I showed also how to do that, and then to estimate the thickness of the tribofilm formed during the sliding or rubbing context. Now, predictive model which we are trying to make is really helping us to formulate the lubricant, low viscosity, high viscosity, what kind of formation of the additives could be added, and how do we optimize the performance of the mechanical system. That can be done. For that purpose, we really require data collection and pre-processing. This also was covered in one of the lecture. What we do, we collect the experimental data which can really quantify the tribofilm formation. like whether it's a friction force or whether debris or lubricant deterioration or thermal images, whichever. Because in subsequent to this, and after 2 3 slide, I'll be covering one of the thermal imaging of one of the case studies. So whichever really symbolize our triboform formation, we require those data, we require analysis of that. Like in one of the case study I did using the proxy sensors. Proximity sensor where two sensors are sufficient to provide what will be the film thickness formation. So that can be utilized. Now, this data set, whatever we are doing, need to be analyzed appropriately. Now, we need to also provide all the important features, and we will be doing, as I say, sensitivity analysis to find out which parameters are more important, and that's why we go ahead with the feature selection, because we may get a lot of data. We may get a lot of statistical derivations of that, but will every data be important? For that, sensitivity analysis required, which will be covered in lecture 33. Then we really go with the training and testing. This also been elaborated in an appropriate manner in a previous lecture. We also emphasize on two things. We say most of the algorithm which are in literature, people use MSC only, but we really require MSC as well as a coefficient of determination. These two parameters are really helping us to figure out whatever the model which we are making using regression analysis, is it really correct or not. Sometimes we use a cross validation. In MATLAB I already covered the five-fold cross validation they use, but we can use a two-fold, three-fold, depends on what really require accuracy is there. Finally comes the deployment of the model. When we are exporting after training, we need to predict the film thickness to figure out what will be the weight rate. In one of the case study, I mentioned also that friction measurement as well as a wear measurement or estimation using the predictive model can be done simultaneously, so the judgment or decision making is easier. So that's why we say create precise and trustworthy predictive models for tribofilm thickness, leading to informed decision making and progress in tribology and mechanical engineering. So this is what we really require. This is the overall approach of predictive modeling of a tribofilm thickness, which we have covered in earlier cases. So I'll just cover one of the case, another case study. And we say in this case, earlier there was some issue, like whatever, when we were making a sensor or purchasing sensor, those were costly. Now the sensor cost has come down, data acquisition system cost has come down. So we can do a digital technologies to find out the in situ measurement of friction and wear, and then after getting those data, we can utilize in an effective manner. We don't have to do everything or just take a judgment well in advance. Whatever the data comes, we need to analyze those data, and then we use the sensing technologies to monitor the machine behavior under different condition, whether there is a insufficient or inadequate lubricant. If there is an inadequate lubricant, naturally temperature rise will be there. So either we have a thermocouple or we have a thermal imaging camera, then we can do it. If there is some sort of a change in the load, that also can be estimated easily, because there are many times three bearing which are supporting load, and each bearing or reaction force can be estimated. And then if there is a more shifting of the load of the on a one bearing, that naturally the other bearing has some sort of failure, and that can be giving us some sort of a indication that the bearing should be examined properly. I also covered misalignment. In my view, misalignment is one of the major issue, and almost all the system whatever I have analyzed, there is always some misalignment. Sometimes insufficient cooling, again we say that there is a temperature. Manufacturing defects also will give a higher side of the temperature. So that's why we are going to cover only on the temperature related. That's why this paper, which was published in 2020, say novel methodology for condition monitoring of the gear wear using supervised learning, that already we knowledge having knowledge, using infrared thermography. Again, when we are going ahead with the thermography, it has a number of drawbacks also, but to explain the methodology is good. Many times, if thermography is not done properly or images are not captured properly, it will give wrong signals also. So false signals also, there's a possibility. However, in this paper they have shown 100%, which is somewhat difficult to digest, but there's a, we will try to explain the methodology. So what we say in this case, Earlier there are established method for the gear. You say on the sound acoustic measurement and vibration monitoring are well known tools. Only the problem with these tools is that it cannot really estimate the early detection of the wear. That means they can find out what will be the failure, but they cannot find out what will be the fault. So if the fault creation is happening, unless this propagated to the certain age or certain limit, it will not be diagnosed easily within these two tools. So we need to think about early detection of wear or early detection of the faults. Second is that they were using infrared imaging, which is NDT technique, particularly to detect the temperature variation, which can give some sort of a fault detection. So infrared imaging captured infrared radiation to gauge surface temperature. Reason being, they capture this radiation because every body emits radiation if it is a temperature is above absolute zero. And then if you are capturing and then doing a trend analysis, you will know under which situation it is getting a more problem. So they use a artificial neural network, which we have already covered in earlier lectures. We say identifying in this case hotspot in infrared imaging caused by the gear wear, and then ANN they were utilized for the categorization of the whether the wear has a happening significant 25% failure, 50% failure, 75% failure. So for training purpose they use this one, whether the gear is healthy with a 25% failure, 50%, 75% wear. So they did this kind of analysis, and that's what I'm trying to explain it. So this is what setup they used, and they capture this thermal images. They try to convert the thermal images in thermal matrix to give the results to us, and then based on that they use some sort of normalization. They use LDA, it's like a PCA which we already use, principal component analysis. They have used a linear discriminator analysis to reduce the dimensions and come up with the right features or useful feature. After that they use ANN and then figure out finally whether it can be classified as a healthy gear, 25% failure, 50% failure, 75% failure. What has been written here: continuous monitoring of thermal behavior of the gearbox by recording the thermal images, which they have done through acquisition and processing of the pictures. They get two outputs the way we already have done in our one of the lecture. They get a color image, a color infrared image based on the digitized intensity values, and they get a grayscale infrared image, which can really give a linking to the temperature. This grayscale infrared image is related to the heat matrix. Again, it need to be trained properly to get overall right results. So this is a colored image which we are showing here, and this is a gray image. And gray image is mostly 8-bit in the image. You can see here it can be identified naturally using some sort of a formula, some sort of initial model. In this situation, what they have done something like this. You say the T true, the true temperature, the temperature derived from a pixel intensity can be given as a TC min, T gray, T MGV, and MGV is a maximum. This is a maximum pixel intensity, while this T gray is been derived from this image pixel intensity for the gray image. So this is a maximum, and this is a one. And now here T max, T minimum, we say maximum and minimum temperature related to infrared images. Now these data are required. If you don't have a right calculation, then there will be problems. So this is a what they use this algorithm. Again, this is a supervised algorithm, or again if it is a trained, then only, or maybe it was a correct, then only the results will be correct, otherwise it will not be. So many times we use our own algorithm, we think about some relation and we incorporate that relation into the solution or to the ANN. So this is what already we covered similar kind of thing in lecture 26. You can see we found analog image, digital image, we converted in we say the RGB can be utilized 0 to 255, 0 to 255, 0 to 255, and grayscale can be done in black and white, and this is a 8-bit image. Same thing which they have done, we have already covered into lecture 26. So now again I'm going to try to give the same thing. They have used accelerometer, and this is a thermal imaging camera. And one point comes here, the gearbox has to be open. If the gearbox has a covering, then we really require a number of filters, because we have that in our lab, and we find thermal imaging is not so easy if there is a casing and there are many other things. So noise level will also increase unless we do a lot of filtration and do correction. So in this situation, what they did, they used MATLAB for processing the thermographic images. They use a statistical parameter, they calculate the 10 parameters. Similarly, the way kurtosis, with the skewness, RMS values, those values, and they try to integrate those parameters with the ANN fault diagnosing techniques or classification. So they capture overall, and then they made a database of 200 samples. How they did it? 50 for healthy case, 50 for 25%, 50%, 50 for 50 images for the 50% wear, and 50 for the 75% wear. Now each test which they conducted for the healthy gear, for and then they mounted those gears with 25% wear, 50% wear, 75% wear. Each test was conducted for the 90 minutes. They give first 40 minutes to the stability, because temperature increases slowly. It doesn't happen immediately, it jumps. So they give first 40 minutes for the stability, and then last 50 minutes images were captured. Per image, and then they cover one image in 1 minute. So image rate was a 1 minute per one image 1 minute per minute. And then as I mentioned, initial 40 minutes were kept for the thermal stability. So they have this kind of data set, 200 samples. Once we give a 200 samples and the 4 categories, ANN can classify easily. After that, whatever I take a sample, maybe if it is 35% or 40% something, it will do convergence, and then it will put a one of the basket. So you say now this much is where is happening. So this is a one way to look at. And then to it can be utilized in the film tribofilm formation also, it can be done. To validate what they have done, they compare with the vibration signals, and then they found whatever they have done in thermal imaging, that gives 100% reliability, while vibration gives analysis gives only 81.2% accuracy. So from based on that, they assume that vibration analysis is not as good as a thermal imaging. Again, anything which is 100% to some extent can give overfitting chances. So we need to be very careful, and we need to do iteration. So instead of the 4 basket, if we make a 8 basket or 10 basket, it will give better results in my view. Many times, because we are assuming here the film thickness or a specific film thickness is lesser than 3, and if the wear rate is happening much faster, which can be calculated, which can be estimated, we can give some sort of regression formula using this kind of analysis, it can be done. However, more and more depth is really required as we are progressing. What we did in 2009, now it becomes redundant. Now 2024, we really required many good things to be incorporated, because we have very good software, we have a good sensors, and more accurate analysis as possible using this one. So with this, I say thank you for attending this lecture. Thank you.